When some aqueous solution of sodium carbonate is added to a dilute solution of sodium chloride, what happens to the pH of that solution? Now, what's important here is to think about the hydrolysis of these two salts. Sodium chloride comes from sodium hydroxide and hydrochloric acid. That is a strong acid and a strong base, so that's going to be neutral. So the pH is already at around 7. Sodium carbonate comes from sodium hydroxide and carbonic acid, which is H2CO3, and it's a weak acid. That means that this particular salt over here is a basic salt. That means that the pH is going to go towards basic. But what does that really mean? pH is going to increase because basic is above 7. So then what's going to happen is that pH will increase. When hydrogen chloride gas is dissolved in water, an equilibrium is set up and can be represented by this equation over here. Now, identify your Bronsted-Lowry bases. Hydrogen chloride loses a proton, is a proton donor, so that is acid 1. And then when it's donated that proton, it becomes base 1. On the other hand, the water is going to gain a proton, so it is a base, and base 2, and when it has gained that proton, it becomes acid 2, and that's your labeling of your acid, your Bronsted-Lowry acid-base pairs. Differentiate between a monoprotic and a diprotic acid and give an example of each. Monoprotic means that it has got one proton to donate. An example, HCl. Diprotic means it's got 2 protons to donate, which means something like H2SO4, or if you like, you could have said carbonic acid, which we just worked with a little bit earlier. Write a balanced chemical equation to show the ionization of methanoic acid. Now, methanoic acid, when it ionizes, is going to have to react somehow with water. So let's put that methanoic acid into some water. So it's going to be HCOOH, and this hydrogen is going to be involved in the ionization. Add some water, and you're going to get H3O+, because the proton gets donated, plus you're going to get HCOO-, and that is the forming of ions of methanoic acid. It doesn't go very well because it's a weak acid. Solution of methanoic acid with a certain concentration conducts electricity, but not as effectively as nitric acid of the same concentration. Give a brief explanation for this observation. Well, as I just said, your methanoic acid is a weak acid, therefore you form very few ions, and therefore it can't conduct electricity very well. Nitric acid, on the other hand, is a strong acid. What does that mean? Strong acid means that it ionizes very well or forms lots of ions. It's going to form H3O plus and NO3 ions, and lots of them, and therefore you're going to get H as a good conductor. Define a standard solution. Bookwork, it is a solution of known concentration. Differentiate between a strong and a weak base and give an example of each. A strong base will dissociate very effectively in water, making lots of ions, whilst a weak base will dissociate poorly in water, making few ions. There's one weak base that doesn't dissociate, that is your ammonia. And ammonia is going to ionize into NH4. So it does not do that very effectively. So you could have used that as an example. So strong bases include sodium hydroxide, potassium hydroxide, lithium hydroxide, whilst weak bases are going to include things like magnesium hydroxide, beryllium hydroxide, calcium hydroxide, ammonia, aluminium hydroxide. A standard solution of sodium hydroxide is made by dissolving 1,5 grams of sodium hydroxide in enough water to make up a certain exact volume. Calculate the concentration of that solution, and then we're going to use it to work out a titration. So first let's get the concentration. Number of moles is equal to mass over molar mass. We need the molar mass of sodium hydroxide. So that's going to be 23 plus 16 plus 1, and it turns out to be exactly 40. And then you've got 1,5 divided by 40, because they gave me 1,5 grams over here, and I land up with 0,0375 moles. That needs to be dissolved in that volume, so concentration is equal to number of moles divided by volume, which is 0,0375 divided by 0,25, because I had to convert the 250 centimeters cubed into decimeters cubed, and I land up with 0,15 moles per cubic decimeter. Number 21, we've got 20 centimeters cubed of sodium hydroxide, and it's titrated against methanoic acid, and we need to determine the concentration. I've got sodium hydroxide plus methanoic acid will form HCOONA and water. This is what's useful about this particular reaction, is that it's a 1:1 in terms of ratio. So when I now say number of moles of acid over number of moles of base equals concentration of acid, volume of acid, concentration of base, volume of base, this is 1:1. Then I've got my concentration of acid is what I'm looking for. My volume of acid is 25. My concentration of base is given to me 0,15, and my volume of base is given, and the concentration of the acid turns out to be 0,12 moles per cubic decimeter. Would the endpoint of that titration be acidic or basic? Well, I've got a weak acid and a strong base, so I'm going to have a basic endpoint. Why? Because it's a titration between a weak acid and a strong base. And what indicator would be suitable for that titration? When I have a basic endpoint, it's going to be your phenolphthalein. Remember, if it was an acidic endpoint, it would be methyl red or methyl orange. If it was a neutral endpoint, it would be bromothymol blue. Could be litmus, but bromothymol blue is better. If sodium methanoate were dissolved in water, what would the approximate pH of the solution be? So now if I just took sodium methanoate, what did it come from? Sodium methanoate was derived from sodium hydroxide and methanoic acid. So sodium methanoate is as if I stuck a strong base and a weak acid together, so it would have a pH of plus minus, let's say, I don't know, slightly basic, so let's go with 9. If you said 8, I'd accept it. If you said 10, I'd accept it. It's not going to be 14. It's going to be a little bit closer to neutral than that. What is the autoprotolysis of water? Write a balanced equation for the reaction. Autoprotolysis is when water breaks up into its constituent ions spontaneously. And the balanced equation for that is going to be 2H2O becomes OH minus plus H3O plus. Then we get asked to differentiate between an oxidizing agent and a reducing agent, and an oxidizing agent and a reducing agent. This is just pure definitions again. Oxidizing agents, you're going to look at your oil rig, and your oxidizing agent gains electrons, your reducing agent loses electrons, which is different because remember, oxidation is loss of electrons, but the reducing agent is oxidized, and the oxidizing agent is reduced. Reduction is the gain of electrons. So you just need to get all of that straight in your head, and it works out fine. In both cases, electrons are transferred, and the electrons are transferred from the reducing agent to the oxidizing agent. Identify the oxidation and reduction reactions in the following. So first, zinc is on its own 0, fluorine's on its own 0, zinc is always plus 2, fluorine's always minus 1 because it's in group 7, and that turns out to be neutral. Why? Because there are 2 minus 1s and 1 plus 2, so that's naught. Then we're going to identify our oxidation and reduction. Zinc goes from 0 to plus 2, so that is an oxidation, and fluorine goes from 0 to minus 1, so that is your reduction half reaction. Number 27. What type of bonding takes place in zinc fluoride? It is a metal and a non-metal, and a metal and a non-metal is going to land up being an ionic bond. You don't have to worry too much about the electronegativity difference. The metal non-metal is probably good enough. You could have worked on the electronegativity difference as well.